Baldovino of grade 11 Sir Isaac Newton of Rizal National Science High School, and I'm here to teach you about discontinuity. Let us visit our partner to help us out. Cyruz!
Gotcha! Just like what Jorlyn said, I'm Cyruz Ulang of grade 11 Sir Isaac Newton of Rizal National Science High School. So I will help her to teach you about discontinuity.
And by the way, we're doing this tutorial in partial fulfillment of our project in basic calculus, but mostly we're doing this to help you out in understanding the lesson. Our objectives for today are to: number 1, know the meaning of a discontinuous function. Number 2, help you determine whether a function is continuous or discontinuous by just looking at its graph. And number 3, identify and understand the 3 types of discontinuity and their graphs. Okay, here's Cyrus Ulang to give you a head start with the lesson.
Come on, let's start!
A function is said to be discontinuous if there are any holes or breaks in their graphs. This is an example of a discontinuous function, while this is an example of continuous function where you can see no breaks or holes.
In order to determine the continuity of a function, it must satisfy 3 conditions. First, f of c must exist. Second, the limit of f of x as x approaches c must exist. And last but not the least, f of c must be equal to the limit of f of x. For example, let us find out if f minus 2x is continuous at x equals 1. Let us find f of c by simply substituting x to the function. Let us then find out the limit of the function. Since it is a linear function, we can easily find the limit without algebraic manipulation. There are 2 ways in knowing the limit. First is through table of values, and second is through substitution. Let us use the substitution method instead. Let's determine if f of c is equal to the limit. As we can see, they are indeed equal. Hence, 5 minus 2x is continuous at x equals 1. However, if one or more conditions are not satisfied, then that's where discontinuity comes in. There are 3 types of discontinuity: the removable or whole discontinuity, the jump essential discontinuity, and the infinite essential discontinuity. Let's start with the removable or whole discontinuity. A function f of x is said to have a removable discontinuity at x equals c if a. f of c and the limit of f of x as x approaches c exist, and b. f of c is not equal to the limit of f of x as x approaches c. For example, let us find out if the piecewise function is continuous. Let's find out f of c by simply finding the function that has an x equal to the c. If there is a numerical value, then it means f of c exists. Then, let's find out if the limit of f of x as x approaches 3 exists. As we can see, both f of c and the limit of f of x as x approaches c exist. However, they are unequal. The graph looks like this, and we can see that there is a hole at x equals 3. What can you say about this, partner?
I think we can remedy the discontinuity, partner.
We can remove the discontinuity through redefining the function. As we can see in the graph, there is a hole in the line, and we can solve it through letting f of 3 be equal to the limit of the function. The new piecewise function, or the continuous counterpart, will be, and look, There are no more holes. And that's how we redefine the removable or whole discontinuity.
Alright, thanks again, partner. So moving on, let us talk about the second type of discontinuity, which is the jump essential discontinuity. Jump essential discontinuity looks like this, wherein the right and left hand limits both exist but aren't equal to each other. For example, in order to get the f of t, we need to look at the function which has the equal to the value of x, and that is the first function. Simply substitute the given x to the function and voila! We already have the f of c. Let us now get the limit of the function as x approaches 3. But first, let us get the left and right hand limits. We will use the function 2x for the left hand limit since it includes the values less than 3, while we will use the function x plus 4 for the right hand limit since it includes the values greater than 3. Since the left and right hand limits aren't equal, meaning the limit of the function does not exist. The graph looks like this, and we can see that there is a break at x equals 3. Hence, we can conclude that f is discontinuous at x equals 3 and it has a jump essential discontinuity. Am I right, partner?
Yes, that's right. Unlike removable discontinuity, we don't have remedy for jump essential discontinuity. So let us move on to our next topic. Let us discuss now the last type of discontinuity.
Infinite essential discontinuity, or known as asymptotic essential discontinuity. There is a vertical asymptote. The conditions for this type of discontinuity are: this type of discontinuity mostly happens on rational functions. We can stop right there and conclude that f is discontinuous at x is equals to 2. But let's continue and prove that the limit of the function doesn't exist. And now, we can conclude that f is discontinuous at x is equals to 2, and it has infinite essential discontinuity.
Now we've reached the end of the discussion proper. Here's a flowchart to summarize the lesson.
And a 5-item assessment. First, you have to determine what the point and type of discontinuity based on the graph.
These are the following solutions.
Once again, I'm Cyruz Ulang from grade 11 Sir Isaac Newton of Rizal National Science High School.
And I'm Jorlyn Baldovino of grade 11 Sir Isaac Newton of Rizal National Science High School. Thanks for watching, and we hope you learned something about discontinuity. See you next video, and remember to stay curious and never stop asking questions.